Direct current is used in the simplest form of circuits, and it's pretty straightforward to understand. So what is it and how do we use it? Let's find out. Hi, I'm Grant and welcome to the 9th class in the AGK series. Today we're going to be having a look at all things to do with DC electrics. We'll have a look at how to generate, store and then use that electricity and see what sorts of things we could do with this simple form of circuit. DC circuits are simple and the energy source for DC can be stored in the form of a battery, which makes them portable. So simple light aircraft will use a DC circuit with batteries to provide electrical power. As aircraft get bigger and require more electrical systems, usually an AC system is used as well. But for now, let's just think of a small, simple aircraft with batteries for its electrical power system. Batteries store electricity in a chemical form. And in a battery, there are normally multiple cells or sections. And within each cell, there are two plates of different materials, usually metals, called the anode and the cathode. In between them is a chemical solution in liquid or gel form, which allows the flow of charged particles from one plate to the other when the battery is connected to a circuit. The type of liquid, as well as the material used for the plates, determines the voltage output of each cell. And when combined those cells together, you get a voltage output for the battery. Basically, what happens is a chemical reaction occurs at the anode, where electrons are released. And the cathode collects those released particles, and that makes the electricity flow. It makes charged particles flow from one plate to the other. Eventually, though, the anode and the cathode reach the point where they are unable to release or accept any more electrons. This means that there is no more room for the electrons to flow. This is when the battery would be said to be fully discharged or flat. The amount of time it takes to do this can be described as its capacity, which is given in terms of its amp hours. Basically, the amount of current in amps that it can sustain for a certain amount of time. So say, for instance, we had a 20 amp hour battery. It could do 20 amps for 1 hour, or it could do 10 amps for 2 hours, because that makes 20 amp hours. Or any combination of amps and hours that make up to the total of 20. When we're flying an aircraft, we can't exactly go out and get some new AA batteries and put them in a slot somewhere in the aircraft like you would with your TV remote when these batteries go flat. So we must have the ability to recharge these batteries. If you can recharge the batteries, we call the battery a secondary cell battery. And if you can't recharge them, it's called a primary cell battery. So something like your AA batteries would probably be classed as primary cell batteries, whereas something like your car battery is a rechargeable battery, so would therefore be secondary cell battery. With a secondary cell battery, we can basically reverse the flow of electrons within the cell so that the electrons are released from the cathode and accepted back by the anode until all the electrons are returned to their original place. We do this by applying a voltage to the battery which is more than the voltage output of the battery, usually by about 10% more. In an aircraft, we use a device called an alternator to do this, which is essentially a small electrical generator which uses the spinning of the drive shaft of the engine to create a voltage just large enough to charge up the batteries when they need it. For the ATPL exams, there are three main types of battery primarily used in aviation, which are all made up of secondary cells. The first is a lead acid battery. These are the oldest of the three types. The plates are a lead composite material, and the liquid in between the plates is a diluted sulfuric acid. Sulfuric acid is quite a reactive substance, meaning that about 2 volts per cell can be produced. However, lead is heavy, and flying around with heavy and highly reactive, unstable acid is not good, especially if it leaks. This can lead to problems with other components potentially reacting with that acid and failing. Because of this, nickel-cadmium batteries were designed. So NiCad batteries, as they're often called, have a nickel and cadmium composite material for one plate and a different nickel composite for the other plate. They're both submerged in a potassium hydroxide gel, and this substance isn't as reactive, so only about 1.2 volts is produced per cell. However, these batteries are lighter, more stable, and they don't come with the risk of acid leaking out onto key components of an aircraft. The third type is lithium-ion batteries. These are the batteries that most modern electronic devices use, like phones and laptops, and they have a very high energy density, meaning that for their weight they produce a lot of energy, about 3.7 volts per cell, although I've seen quite a lot of variance on this figure. Anywhere from between like 2.5 to about 4 volts is what I've seen. So 3.7 seemed to be one that I saw quite a lot. They do, however, suffer from a phenomenon called thermal runaway. This is where the cells in the battery essentially overheat, which is mainly going to happen during recharging. The runaway element refers to the fact that only one cell on the battery needs to overheat, and then it overheats the next one, and so on and so on. And this leads to the fire that can sometimes be caused by a thermal runaway situation to potentially keep burning for a very long time. You think you've solved the problem and reduced the heat in one cell, only for that overheat in one cell to trigger an overheat situation in the next cell, and so on and so on. And for this reason, these batteries must be carefully temperature monitored and placed in fireproof casings. Some manufacturers, though, see this as too high a risk, so stick to the older, more thermally stable NiCad batteries. So once we have a circuit powered up with a battery, we want to use some of that electrical and chemical energy. And one of the most common uses is to turn a motor. One of the fundamental concepts we need to understand before we look at motors is that a magnetic field is created around a wire when we pass a current through it. This is because the electrons that go through that wire or ripple through that wire have a negative charge and therefore produce a magnetic force. It's an electromagnetic force. They're both sides of the same coin, if you like to think about it that way. The more electrons we end up putting through a wire, aka the higher the current, then the stronger the magnetic field that is created. And it does this in a specific pattern, which I like to use my right thumb for. I put my thumb up to indicate the current flow, and my fingers wrapping around indicate the direction of the magnetic field surrounding that wire. And the direction is the way that the north pole of a compass would be attracted to. Or if you imagine the wire standing straight up through the center of a piece of paper like this, then you were to take some iron filings, place them on the bit of paper, and send a current through the wire, you'd see a circular pattern of iron filings formed by the magnetic field in that pattern of wrapping around the wire like that. Now I know it's a bit weird because a circle doesn't have a direction, but that will all become clear soon. And we can use this electromagnet created by the current through the wire to attract and move other magnets, maybe to push a switch or move a valve, which is sometimes referred to as a solenoid. If we take our wire with current flowing through it and place it next to a stronger stationary magnet, then the two magnetic fields, one by the magnet, one by the wire, will interact with each other. And this will cause the wire to move, just like if you put two normal magnets next to each other. And if we make a loop of wire and put it inside a U-shaped permanent magnet, then we can start to see the beginning of how a motor works. Let's start in a position where we have a loop of wire lying flat inside this U-shaped magnet, with this as the north and this as the south side of the permanent stator magnet. When we send current through the loop, it can get a bit confusing because the wire will start to move because there's two magnetic fields interacting with each other. But luckily for us, we have our left hand. First of all, we take our first finger and we point in the direction of the permanent field, which is going to be there, north to south. First finger is the field. Then we take our middle finger and point it in the direction of current flowing through the wire. So positive to negative. We'll look at this red side first. The current is flowing this way, up and to the left. Then we put up our thumb, and our thumb points to the motion. So in this example, our wire would rotate down the way on the positive side, and if we flip things round, we've got our field, we've got our current flowing back into the battery here, and the thumb comes up. That means that it's going to come up on the blue side. So we've started off motion in a motor, which is a good thing. But if we attach this side of the loop of wire to a positive side of a battery, and this one to the negative side of the battery, then everything starts off fine. But as we reach a half rotation though, our hard connection to the positive side means that the current is now flowing this way. So it would cause a downward motion. And in the blue, our current flows this way, which would cause an upward motion. So we get into this situation where we've got the motion changing direction. So you'd get a motor that just does this all day, which is not what we want. We therefore need to change which leg of the loop is powered to and connected to the positive side of the battery and which is connected to the negative side of the battery to ensure a constant direction of current through each section of the loop that is influenced by the field. The key is to do this swap at the correct time through a device called a commutator and create a seamless rotation of the loop of wire. A commutator is essentially a ring of conductive material with little gaps in it. The gaps stop the current flow at the correct time and switch the arms of the loop around. And to keep electrical contact with the rotating ring of the commutator, little conductive brushes are used to keep contact with the surface, but these do wear down quite quickly, relatively quickly to some other components. So this is often the first point to fail in a motor, these little brushes. To optimize our motor further, we can put in more loops of wire. If we put another loop of wire offset by 90 degrees, for example, and then enhance our commutator, we can have a current flowing through both of those loops at the correct time. And as the first loop reaches sort of a dead zone, the other one is in the area where it feels the highest force, and that keeps the motor moving along with a high torque level. And we can keep adding more loops and more loops to keep this thing as efficient and increase its efficiency as much as possible. We can also use electromagnets for the non-rotating stator element of the motor as well. This allows us to control the strength of this electromagnet by letting current flow or restricting it. If we use the same power source as we do for the loop, then we can either connect the electromagnet in series with the stator, well, the stator and the rotor can be in series, or the stator and the rotor can be in parallel. Let's look at series first, which is over here. We use a stator with low resistance, a low resistance electromagnet, and this creates a high current. This high current produces a strong magnetic field in the stator, and it does so immediately, which means we get a high starting torque force. The motor, however, can overspeed though, unless controlled carefully through current regulation or simply by restricting the torque output through mechanical brakes and things like that. This is a common setup for things that require a short, sharp burst of power, like a starter motor on an engine. In contrast, we can use a parallel setup, which is called often a shunt motor. And this uses a high resistance for the stator magnet. This causes quite a low current flow. That means a weaker magnetic field and a lower torque turning force, but it has the benefit of a constant speed because the difference between the two magnetic fields is not that great. This type of arrangement is for things that require a long sustained output like a fan for a ventilation system. What we can also do is we can combine both of them and get a motor that has two electromagnets, if you like. You've got one that's in parallel and one that's in series, and depending on the use case, you can have a high torque or you can have a constant speed, and you would just call that a combination motor. To boil things down though, if you've got a series, expect a high torque, and if you've got a parallel wound electromagnet, expect a constant speed. Or as I say, a combination of both of them, we'd get both benefits. A battery is a way to store electricity, but what if we wanted to create electricity? Well, we use a generator. We know from the motor section that we just looked at that if we pass an electrical current through a wire and place that wire in a magnetic field, we cause motion. The reverse process of this is also true. If we cause motion in a wire within a magnetic field, we cause current to flow within that wire. A generator is essentially a motor working the other way around. In a generator, to make sense of the motion and current induction, we use another quick method with our hands. So for a motor, we use our left hand, and for our generator, we use our right hand. To remember it, I just exaggerate it and say generator, and the fingers mean the same things. First of all, we point with our first finger in the direction of the field. Then we use our thumb for the motion, and the current is the middle finger. So for this example here, we've got the field, we've got our motion coming up the way, and our current goes in from the positive to the negative. Simple. Simple generators will use permanent magnets for the stator, much like a simple motor, and the amount of current induced in that wire would depend on the speed of rotation and the strength of the magnetic field, and of course the number of loops of wire within that magnetic field. When using permanent magnets though, it does sort of run into a few problems. Because we've got to use a permanent magnet, it does normally mean that the magnetic field created by it is quite small, so that it doesn't interfere with other things when it's not actually in use as a generator. Therefore, these simple motors are only used for very low output devices. The output current is controlled by a commutator. Remember how it controlled the switching of the current between each leg of the loop in a motor? Well, now it does the same thing. It basically ensures that the current output switches from leg to leg of the loop, and it keeps the current flowing in the same direction once it reaches the output circuit. So because using permanent magnets means a weak magnetic field and probably a low output current and voltage, we generally want to use and do use electromagnets for the stator in a generator. This way we can increase the output voltage because we can make the magnetic field stronger, and we can also switch these off whilst they're not in use and do not cause disturbances to other systems on the aircraft. However, this is an electromagnet, so we do need another source of power to create the magnetic field in the first place to begin the generation process, like a battery or something. But once the generator is up and running, we can just tap into some of the electricity generated and power up the magnetic field from the output of the generator itself, hopefully that makes sense. Like with a motor, we can connect the stator electromagnet in series or in parallel with the output loop of wire and the output voltage and current. For a series setup, we use a high resistance wire for the stator, much like in a motor, to control current flow. And in this setup, if we rotate the rotor faster to generate a higher current, then the current in the stator also increases, and that means a stronger magnetic field, and then it sort of builds and builds and builds, and it means more electricity flow the faster the loop of the generator or the rotor of the generator spins, and it grows exponentially like that. So you've got a higher load output and a higher voltage and current in the electromagnet as well. They both grow. With a parallel setup, as we add more resistance to the circuit on the rotor side of things, the usable electricity, if you like, the components that we want to power up from this generator, then the total resistance of the current reduces as there's now more ways for the current to flow. Remember that the resistance in a parallel circuit is 1 over RT equals 1 over R1 plus 1 over R2, etc. And if we had a fixed output voltage from the generator, then we might see the current of this circuit shoot up to counteract for more elements and a lower resistance. Too high a current can cause a lot of damage to the circuit, and that's why we have fuses. When they experience too high a current, they blow or break the circuit and stop electricity from flowing. Instead of blowing fuses and ruining the circuit, we don't hold the output voltage at full power and allow it to reduce as more items are added into the circuit, and this controls the current and stops it from getting too high. So with the series setup, we get more voltage as we add resistance to the circuit, but with the parallel setup, we get less voltage output as we add resistance. And remember, we want it to work this way so that the current is held at appropriate levels and it doesn't run away and blow up loads of components. The best thing to do though is to combine both these systems into a compound wound generator, and this means that we get a stable output voltage as we are feeling both the benefits and drawbacks of both systems at work. Okay, so how do we move this electricity around an aircraft? The main way we do this is obviously wires. but there is another important method called bus bars. I like to think of these as literally a bar of metal with wires to all the different systems touching it. And these systems will be wired to the bus bar in parallel so that if one of the components, like a light, fails, it won't cause all the other systems attached to that bus bar to fail as well. And the reason we use bus bars is that it's an easy way to group different systems together. We can essentially group them into different categories based on how important they are for the safe conduct of flight. Then if we have any problems to do with the electrical system on board, then we can ditch loads of systems at once. Which system is assigned to each bus bar is something that a manufacturer will know, and it differs from plane to plane. For example though, if you were to lose all generators on board an aircraft and you only had a battery left to fly on, you might see something like one of the aircraft displays or radios no longer works, but it will always be set up to allow just enough systems left over to land safely, albeit pretty quickly before the battery runs out. If we don't want to ditch a whole set of systems at once though, we can use circuit breakers to control individual systems. This is essentially a reusable fuse. A fuse is just a thin piece of wire that is designed to overheat and melt when a certain value of current goes through it, therefore breaking the circuit and protecting components from getting damaged. With a circuit breaker though, we use two different metallic strips and they're connected within the device itself, this circuit breaker device itself, and when they are connected, it allows electricity to flow. When an excessive current travels through the circuit breaker, then the metals will heat up at different rates, expand and separate. The separating metal strips will push on the circuit breaker mechanism and pop it out, and obviously stop the current flowing. The circuit breaker can be reset, but with caution. Why did it pop in the first place, for example? Probably because the level of current flowing through the circuit was unsafe. And circuit breakers can also act as switches for systems on board that don't have a physical button. For example, the fire protection systems in a jet engine aircraft don't have an on-off switch. They are always on if the aircraft has electricity so that they can be used immediately. If we have a fault in one of these systems though, and engineers need to work on the system, they can pop a circuit breaker and therefore the system will have no power and work and maintenance can be done on it safely. It also helps if you have problems on the ground that are pretty minor. You can reboot the system by popping the circuit breakers and then resetting them, basically giving it the old on and off again treatment like we do to our computers at home. In summary then, a battery uses two plates of a material in some sort of liquid or gel solution. One of the plates causes kind of corrosion, and the other one is deposition of electrons, and that flow of electrons and charged particles can lead to electricity flow once you connect a load to it. In aviation, there's three main types of batteries. All are secondary cell batteries. Secondary cell meaning they can be recharged, whereas primary means they can't be recharged. And to recharge, you normally add a voltage back to the battery about 10% higher than the battery is rated for. So the three types are lead acid, producing per cell about 2 volts, but lead is heavy and there's highly corrosive acid on the inside, meaning that if there's leaks, that acid can corrode other components, which is not ideal. The evolution of this is a NiCad, nickel-cadmium battery. The nickel-cadmium plates are lighter, and there's also no risk of acid leaking because it's quite a gel-like material and the acid isn't as reactive, so generally a bit safer and better than lead acid. We also have lithium-ion batteries. These are modern batteries that you find in phones and tablets and stuff. They're very energy dense. They produce a lot of voltage output per cell, but they do suffer from a phenomenon called thermal runaway, where one cell overheats and it causes the next cell to overheat, and so on, and that normally happens during recharging. With a motor, we generate an electric field in the stator magnet and send a current through the loop of the rotor, and those two magnetic fields interact with each other to cause motion. We want to use our left hand when we're talking about motors. Our first finger points in the direction of the field, Our middle finger is the current. So for this example, the red side would be like this, and our thumb is the motion. So our thumb is going to go down and show that the red side goes down. And if the blue current comes back this way, it's going to go up like that. Once we get to a half rotation, if we have a hardwired connection, our current would essentially be flowing the other way, and it would cause our motor to rotate back on itself, and we just get this sort of flip-flopping of 180 degrees, which is not what we want for a motor. So we use a commutator device, which essentially swaps which leg of the loop is positive and negative, and ensures a continuous rotating motion of the motor. To generate the electrical field in the stator, we can use electromagnets. And in a motor, if we wire that electromagnet in series with the rotor, we get a high torque output. And if we do it in parallel with the rotor, we get a constant speed output. Or we combine them and get the benefits of both. A generator is essentially the reverse process of a motor. We spin the rotor to generate the current flow. Remember, we're using our right hand for this. And if we take this example, we're field this direction, the motion, we're going to go down on the red side. That means the current is going to flow this way. And if we look at the other side, first finger's the field, thumb is the motion, current flows this way. So we're actually getting the reverse current flow if we're thinking about a generator in this example. That's why it's left hand and right hand, because the motion is going to change and be different. Hopefully that makes sense. Right hand generator, left hand motor. Where was I? So the magnetic field in a generator can be generated from an electromagnet, and we can use the generator to provide the electricity for that magnet after an initial burst from a battery or something like that, once the the generator is up and running. We can wire that electromagnet in series or in parallel. In series, we get a voltage rise as the current output rises, and with parallel, we get one that falls. So essentially what we want to do is we want to combine both of them and have a compound wound generator to get a steady output voltage from the generator itself. Distribution we just looked at, we use bus bars to section off components, and then as we get failures we can lose a whole bunch of components at once. Or if we want to be more specific, we can use circuit breakers. Two different metals interact. As the current flows through and they get too hot, they separate, breaking the circuit, and we can reset them or use them as switches with engineering approval essentially.